Hey Royals, in this video we're going to look at the idea of sound. So we'll start by looking at our human ear and how we can pick up sounds. Then we'll move into how we can change the speed of sound by changing the medium that we're traveling through or even the temperature. So let's start with that human ear. So our human ear can pick up sounds anywhere between 20 hertz and 20,000 hertz. So if we're below, I'm just going to put here, below 20 hertz, we define that as infra sound. So that's just sounds that are below our threshold that we can hear. And then if it's above this 20,000, we call that, so we're going to say above 20,000 hertz, we call that ultrasound. And we're not going to spend a lot of time on the idea of infrasound or ultrasound because we can't actually see them or hear them. But you may recognize that idea of ultrasound for looking at pregnant women's bellies or looking at an area of your abdomen. Okay, so how do we define the intensity of sound? How intense is that sound that we're hearing? Well, there is a range that is called the pain threshold. And so how do we define that? So the sound intensity is measured in a unit called a decibel. And anything from about 80 up to about 140 decibels is actually painful to the ear if we hear it for long periods of time. And this is why our construction workers or anyone that's working with heavy machinery like a jackhammer should possibly be wearing some ear protection. And so if we were to look at this scale, you'll notice that it goes up by factors of 10. And this is called a logarithmic scale. And so something with an intensity of, say, 10 decibels really means that it's 10 times louder than the thing that came before it. So a conversation versus a whisper. A whisper comes in at about 20 decibels, while a normal conversation comes in at 60 decibels. And that change in just 40 decibels is in fact 10,000 times louder. So if we look down here at a watch ticking, every time we move up that scale, it is 10 times louder, right? So you can see that if we get up to that normal conversation or loud talking, which would be 60 decibels, we are in fact about 10,000 times louder. Now, how does our human ear pick this up? Well, let's discuss first what the human ear is made up of. It's made up of three functional parts. The outer part of our ear consists of, that earlobe and funnel that takes all the sounds that are happening in our atmosphere, and they send them down our ear canal. So that's the first job, that we can get our sounds coming down our ear canal. Once we get to the middle ear, and that's this part down at the bottom in my drawing here, this is the middle ear, you're going to find the eardrum. And these sound compressions that come in, and we'll look at that in a second, this here, the sound that's coming in is going to cause our eardrum to vibrate. And inside the eardrum, the bones will amplify that vibration, making it louder for our ear to pick up. And then we move into the inner ear. And that's in here. We have tiny little hairs inside our inner ear, and they will resonate at certain frequencies. And we call that the fundamental frequencies of these hairs. And so hairs that are a lot shorter will pick up sounds that have a higher pitch, right? So you'll be able to pick up different various sounds based on the lengths of your hair. And this goes with age. As we get older, these hairs, start to fall out and they start to degrade. And so our hearing on the upper and lower frequencies starts to diminish. And that's why we see when we visit grandma and grandpa, they have a hard time hearing us because these inner ear hairs have, fallen out or they've come to be used. Okay, so they take these vibrations from those little hairs and they send them to your brain so that your brain can actually decode that information and tell you what you actually heard. So let's talk about that speed of sound. How does sound move? Well, any mechanical wave, which sound is a mechanical wave, is determined by two things. The first one being the mass of the particles in that medium. So the heavier the mass, the slower the speed. And that totally makes sense. If we had a bunch of bowling balls attached by a string and we tried to move the wave down that string, it would be a lot harder because the bowling balls have more, inertia and they don't really want to move very much. So the sound wouldn't move down that string very easily. However, if you had a bunch of ping pong balls, you could send the information a lot quicker. Now, the second piece that determines the speed of a mechanical wave is the link between the mediums. And so we know that a solid has a strong link between molecules, and a gas, the molecules are further out from each other, and so the linkage between them is a lot weaker. And so stronger linkage means that the sound will travel a lot faster, which makes sense when we think about how fast sound travels in solids versus gases. Well, the sounds that we're hearing with our human ear are not really the vibrations in solids or liquids. We're not really worried too much about those because on a given day, we're talking in air, and air is a gas. So we're going to talk a little bit about the speed of sound in gases. And so nitrogen gas and oxygen are molecules that make up most of our atmosphere here that we live in. But you might be curious about this helium, that if it's in a balloon, and why helium is perceived to increase the frequency or the pitch of your voice. Many people think that this is due to the fact that when you inhale helium, the pitch of your voice increases or changes. Well, in fact, it doesn't. Your vocal cords vibrate at the same rate, but helium allows the sound in your lungs to travel faster. And this is because helium is a much lighter particle and allows the sound to travel at that increased speed. And so when it travels faster, it changes the resonance of your vocal tract, making it respond to higher frequency sounds. And so your voice actually increases in pitch because the speed inside your lungs is increased. So that dictates the fact that, okay, that might be one way to change the speed of sound, but temperature also has an effect on how fast our sound travels. So you can see the picture here on the right hand side. In colder air, speed will actually travel slower. And in warmer air, the speed of sound will travel much quicker. And you can actually cause the speed of sound or cause your sound motions to miss objects just due to the fact of a temperature difference. So if this lazy dog that was sleeping is sitting here and you had cold air above you and warm air off the ground, the sound would actually bend upwards and not reach that dog. Now let's flip the situation and say that the dog is sitting there and the ground is cold and the air above it is nice and warm. Our sound molecules, if you're yelling at the dog, would actually bend downwards towards the ground, and you could actually communicate with that dog. So on a warm summer day, you might experience this, where the air is warm and maybe the concrete hasn't warmed up yet, and you're trying to yell to your friend that might be further down the beach. They might not be able to hear you due to the fact that your sound would have maybe bent away from them. So how do we define this? Well, there's an equation that will support us here. So the speed of sound is 332 meters a second, and that's at 0 degrees Celsius. And so as the temperature increases, there's this factor of 0.59 meters a second for every degree Celsius. And so that's a constant that will be in play. And we have to simply substitute in the temperature of the atmosphere or the location that you're living in. And when we do that, we can actually calculate fairly accurately the speed of sound. So let's look at a few examples of this. So if I had a foghorn and I heard a ship it was coming from a ship that was 2.5 kilometers away. So D is going to be 2.5 kilometers away. And it takes 7.45 seconds for this sound to arrive at you. So we'll say delta t is 7.45 seconds. We can calculate the velocity of this sound. And so we want to know what is the temperature of this sound. So we'll go back to early kinematics with no acceleration. We'll say that the velocity or speed of something is the distance that it travels divided by the time. And so if we substitute in our numbers, and we'll put our distance into meters, so 2,500 meters, and we divide by that time of 7.45 seconds, we get a speed of about 335.57 meters a second, which is great. So the speed of sound at this particular place where you're hearing this foghorn is about 335 meters a second. So let's use this equation that we had above to find out the temperature. So we'll say V is equal to 332, and I'm just going to drop units just so that we don't get bogged down with our units here. I'll multiply by my constant of 0.59, and then we'll have our temperature there. So let's substitute in the speed of sound that we had. 335.57 is equal to 332 plus 0.59 t. All right, so if we substitute or subtract 332 from both sides, we get that the difference in our speeds here is 3.57, and that's going to be equal to 0.59 t. Let's divide both sides of our equation by this 0.59, and you get 6.05, and that will actually be in degrees Celsius. So we get about 6.1 degrees Celsius. So it's fairly cold at the time, but you can determine fairly accurately the temperature of the atmosphere or the location that you're living in based simply on how fast the sound is moving. So let's look at another example here together. So the second example is that you hear a thunder 6.0 seconds after you see lightning. So that's our delta t. So delta t is 6.0 seconds. And you know that the air temperature is 21 degrees Celsius. And I want to know how far away is that storm. And so a kind of rule of thumb is that people say, well, it's about a second. For every second, it's about 1 kilometer. So let's test that. So let's find out, based on the temperature and the time, how fast is this moving? Or how fast is sound? So 332 meters a second, so I'll actually put in my units this time, times 0.59 meters a second per degree Celsius times our temperature. And our temperature was 21 degrees Celsius, so we'll substitute that in, meters a second plus 0.59 meters a second per degree, I wrote squared, second, per degree Celsius times this 21 degrees Celsius. And you work that through, you're going to get a speed of sound, and I'll use a little s here to represent the speed of sound, of 344.39 meters a second. All right, so we know how fast the speed of sound at 21 degrees Celsius is. So we can use, again, the same kind of idea that speed is distance divided by time to find out how far away was that storm. So let's grab a pen here, and we can say that, okay, so if the speed is distance divided by time, then distance is speed multiplied by time. So let's substitute in our values. So we have 344.39 meters a second, and it took 6 seconds for that sound to reach our ears, which means that the distance between you and that storm is about 2,066.35 meters, or a distance of about 2.1 kilometers, right? So about 2.1 kilometers away, which is okay. It's enough time that you can still run for cover and not get wet. All right, so another piece that goes with the speed of sound is this idea of Mach. So you often hear people saying, oh, that plane's traveling at Mach speed, or 1.2 Mach. Well, what the heck is that? Well, it's the speed of the object. And so we'll use O for our object here. And I meant that to be a highlighter here. So O to be the object versus the speed of sound. So if you are going faster, it's the ratio of your airspeed to the local speed of sound. And if you're going faster than it, you are going larger than what we call Mach. And so there's different forms of Mach. There's subsonic, which means that you're going slower than the speed of sound. There's transonic, which means you're going exactly at the speed of sound. Supersonic, which means that you're going above the speed of sound, but not much greater than it. And then there's hypersonic, which means you're going more than 5 times the speed of sound. And so I have an example here to kind of demonstrate how we can go subsonic or supersonic. Okay, so calculate the Mach number of an aircraft that's flying at 850 kilometers an hour. And the airspeed or the air temperature is negative 45 degrees Celsius. So it's fairly far up there where the temperatures start to drop off. So we're going to say that the speed of the object is 850 kilometers an hour. And if we convert that to meters per second, you get about 236.1 meters a second. So we don't know the speed of sound. So we can calculate that. Let's go ahead and say the speed of sound is that equation, 332 meters a second plus 0.59 meters a second per degree Celsius times our temperature. And our temperature is negative 45 degrees Celsius. So 332 meters a second plus 0.59 meters a second. Oh, I always want to put square there. I don't know why. Degrees Celsius. And then negative 45.0 degrees Celsius. All right, so working that through, what kind of temperature do we get? We get that, or sorry, speed do we get? We get about 305.45 meters a second. So you can see that the speed of sound is actually slowing down when we're below 0 degrees Celsius. That's pretty cool. All right, so I can slow speed down by just going below 0 Celsius. So what's my Mach number? So my Mach number is the speed of the object divided by the speed of the sound. If our speed of our object was 236.1 meters a second, and the speed of sound was 305.45 meters a second, then my Mach number here is just simply 0.772. So I'm not yet going transonic. I'm still subsonic. I'm slower than the speed of sound. So in this lesson, we kind of introduced the idea of what is sound, how does our ear pick up sound, and how can we calculate how fast sound is moving at certain temperatures. So if you have any questions or anything on this lesson, please do not hesitate to reach out to me.